Okay, one last thing about improper integrals, and that is to talk about something called the comparison test. And we'll be doing some comparison tests later on in something called infinite series in chapter 10. So it's good to get a little exposure to that sort of thing now. So here we have two functions, f and g, continuous. And the important thing is that the function f, its outputs are always greater than or equal to g of x, which is always greater than or equal to 0 for x greater than a. So if I were looking at the graphs of these two functions for values greater than a, then if this is the function, say, g of x here, the function's f of x is greater than the g of x function's outputs. Or something maybe like that. And then we're looking, again at x equal a on. So let's see if the following makes sense. And these, notice these are improper integrals now, back to the first type we were talking about, where we have infinite limits of integration. And you can see we're going from a lower limit of a to an infinite upper limit. So if the integral from a to infinity of f of x converges, then the integral from a to infinity of g of x converges. And let's see why that's the case. So f of x, right, is the red curve. What does this integral represent? If it converges, it has a value, a finite number. What does that finite number represent? It represents the area under the red curve, right? The area under the red curve, which means that area under the red curve is finite. That area under the red curve is finite. Well, if the area under the red curve is finite, do you see the area under this purple curve, or this curve right here for g of x, that must also be finite. And if it's finite, then this integral converges. Okay. On the other hand, if the integral from a to infinity g of x diverges, then the integral from a to infinity f of x diverges. And so the idea there, if this integral diverges, then the area under this purple curve now, this region under this purple curve, all the way to infinity, right, that is now not finite, it's infinite. It's not finite. And if this area under this curve is infinite, then clearly the area under the red curve must be infinite, making this integral diverge. Okay, so I hope that makes sense. Now, notice the other way around. If the integral from a to infinity of g of x, if I knew that was convergent, if I knew the area under this curve right here was finite, under the purple curve, that doesn't help me know anything about the integral from a to infinity of f of x. Because this is finite, the area under the red curve can still be infinite. You know, this region in between here, we looked at an example of that at the very beginning, where that was the case. The area in between here could be infinite. And so if g of x is convergent, it doesn't tell me anything about f of x. So f of x has to be greater than or equal to g of x in order for me to conclude that if f of x integral converges, g of x integral converges. On the other hand, notice the divergent has to work the other way. At the lower one, right, the one below, if that one diverges, then the one above does. Again, if f of x integral diverges, I don't know anything about g of x. It may or may not converge, the integral from a to infinity. Now, what types of functions can we compare to? Well, it's often nice to compare to p integrals, because we know, based on the value of the p integral, whether or not they converge. And I'll just remind you that we looked at that, right, in a previous video. And we saw that p integrals are this form, 1 over x to the p. Right? If p is greater than 1, then it's converging. If p is less than or equal to 1, then it's diverging. Okay, so we're going to make use of that fact in the following two examples. So, does this integral here converge or diverge? Okay. Well, I think about this function here, and what p integral looks closest to this. I mean, I've got an x down in the bottom by itself, so maybe, you know, you think about 1 over x, right? I mean, maybe that p integral. And of course, that's the p integral where p was equal to 1. Again, the integral from 1 to infinity of this, we actually showed that in the first video that integral diverges, right? If p is, again, less than or equal to 1, then the integral from 1 to infinity of 1 over x dx would diverge. Now, so we know the integral from 1 to infinity of 1 over x dx diverges, right? Because it's a p integral with p equal to 1, right? If p is less than or equal to 1, it diverges. But this only helps, remember, if this is divergent, then we want the function we're looking at to be less than. So I want this to be less than, wait a second, I said that wrong. If g of x diverges, excuse me, if we know this one diverges, right, then the one we're trying to show diverges has to be more, right? So if ours diverges, we want this to be more. And I think it's pretty clearly, since the denominators are the same, look at the numerators, 1 here, 1 plus e to the x. E to the x for values 1 to infinity, well, for any values, e to the x is positive. So for any value of x, 1 plus e to the x is always bigger than 1, right? Because e to the x is always greater than 0. So this quantity is always, in the numerator here, bigger than this one, which tells me I have this inequality. Right? I can say greater than, I mean, it really only needs greater than or equal to, but this is actually strictly greater than, but we'll say that. And then, of course, this is greater than 0. And so we have that connection. We have this integral 1 to infinity f of x, right? And it's greater than or equal to 1 over x, and this integral diverges, right? Therefore, this one diverges as well. Okay, so what we have is the g of x is the 1 over x, right? There's the 1 over x, pretend. Then our function 1 plus e to the x over x, that function would be like the red line. And so by comparison, the integral from 1 to infinity diverges as well. Without any work, right? Now it would be kind of hard, if you think about it, to actually evaluate this improper integral, because finding the antiderivative for this, you know, is a little messy. We have to use, you know, integration by parts to find the antiderivative. It's a little messy. So it's kind of nice just to do direct comparison. Which one do you think we want to compare this one to? Which p integral do you think we want to look at there? Well, if you said 1 divided by x squared, you would be correct, right? Let's talk about this integral from 1 to infinity 1 over x squared dx. What do we know about this? This converges, right? It's a p integral with p equal to 2, right? So in fact, we showed this one in the first video, is convergent. Okay. Now, in order for this to work, then we could say this integral converges if what? If these values are what? Always less than or equal to these values. Right, so go back to our picture. We have basically f of x being convergent, the area, you know, the integral being convergent. So the area under this is finite. And so we want our function to say that this one converges also. We want all these values to be less than, right, and that. So we want our values here to be less than this. Is that true? Let's see. The numerators are the same. This time the denominators are different. What do you say about these two denominators, right? For any value of x from 1 to infinity, notice this denominator here is always what? 5 more than this one. This is x squared. This is x squared plus 5. So this denominator is always 5 more than this one. So if this denominator is more than this one, then what? This fraction here is smaller than that one. You see, if I'm dividing by a bigger number always, this ratio is always smaller. This ratio, so we have this direction of inequality. And so indeed, our values are always less than or equal to this one, since this integral converges. Therefore, the integral from 1 to infinity of 1 over x squared plus 5 also converges. Okay. And that's how we can use comparison tests in certain cases to determine whether or not an integral, improper integral of this particular form converges or diverges.